Hey, my name is Tim Shanerock, and I'm a graduate student at the University of Florida in wireless communications with Dr. Wu. I did my project for this class on the effects of fading parameters in WCDMA efficiency and what changing those parameters would do to the efficiency. So mainly I looked at the bit error rate as a metric to judge all of my testing. So first I started by making a WCDMA channel with a 8 PSK modulation. I'll actually show you this in the code. So there's all my initialization stuff right there. We can talk about that later. Basically, I used 30 bits, but I can program this to be 40 bits per se. And I pretty much just made a random bit stream for the data sets. There are 3 users, so this first part's going to be repeated 3 times. I hard-coded a pseudo random number code because this program that I was using that's built into MATLAB kept giving me the same code for multiple users, and so it wasn't really that useful. So I gave each of the 3 users a separate code. So I spread the PN sequence by the number of bits there were, and I spread the number or the data bits by the number of chips inside this PN sequence, which is 4. So that's what this is doing. And then I XORed them, exclusive ORed, to see which is the similarities and which is the differences in ones or zeros. Then I converted it to a RS-232 voltage. So the 0 bit in logic would convert to a plus 1 volt, and the 1 bit in logic would convert to the negative 1. And just user 1, 2, and 3 right there. Then I added all of the voltages together to create my spread signal in voltage. There's some graphs, and I shifted it a little bit just so I could make it work with MATLAB. And then I send it through a white Gaussian noise channel. I think I set it up with, about 10 dB of SNR. And then I had the option of putting it through a Rician channel or a Rayleigh channel, but for now we'll just keep it at the white Gaussian noise channel to make sure it works. Before I did that, I modulated it. That probably helps. And then I demodulated it, converted it to volts. It was already in volts. And so I multiplied the PN code, which I converted to volts, by the receive code. That's just converting the PN code. I multiplied the two so that I could create an individual signal for each user. And then I took the average. It was kind of like an average every 4 bits, which is corresponding to the 4 chips in the PN code. I would take an average of those 4, and it would give me either a +1 or a -1. And so then I could, what should I call it? I could convert that back to bits from my voltages to be a 1 or a 0. And then I just took a bit error and I summed up all the bit errors at the end. So we can run this real quick. And just kind of show you what all these graphs do. Maybe. Maybe not. Oh, yeah. So yeah, here's a comparison of data 3, the original data that I put in, which was a random bit stream, and the received data at the very end. And as you can see, the BER for each channel is 0, 0, and 0, so that's helpful. Bring all to front. I pretty much did that for each of the 3 channels. Here's just the voltages, and then the voltages being averaged in the receiver. So that should be there. Oh, one more up. This is the spread before and after modulation, so that I could make sure all of the changes were happening between these two, if there are going to be any changes. So in my white Gaussian noise channel, I didn't expect too much of a change since the SNR is pretty high. But when I started adding the fading channels, such as the Rician or the Rayleigh channels, I expected a lot more change between these two, which would in turn make the bit error rates go up a little more than 0. And then this is just data 1, 2, and 3, and then adding the 3 together to create a combined signal. So then we can go to this PowerPoint for a little bit. So this is pretty much everything I just said. How to modulate everything and demodulate it. I ran each case 5 times so that I could take an average of the bit error rate and kind of gauge how well that specific parameter did per the other ones. And I used 8PSK, I don't know, I just used it. Kind of talked about that already. So yeah, here's the voltages added together before and after the white Gaussian noise. It's user 1, 2, and 3. All 3 have bit error rates of 0, which is good. So now we can get to the Rician fading that I used. So Rician fading is a type of simulation you want to use when you want to simulate when there is a target in the line of sight, but there's also reflections from other things that create the multipath effect. So I used a K factor of 10, sample rate of 1 megahertz, and I still use the white Gaussian noise. So basically, I can show you this real quick. Oops. I played around with a couple of the parameters in the Rician and the Rayleigh actually, but one at a time. So I would change the path delays. So I used 1 time or 10 times or 5 times 10 to the negative 7th, 5 times 10 to the negative 6, and then 1 times 10 to the negative 5 for the secondary path delay. And I calculated the bit error rates for all 3 of those, which you can see here. That was just on the secondary path, sorry. The line of sight path I kept at 0. And the line of sight path had a much bigger amplitude of 8 as opposed to 1. So you can see from this that the path that was furthest away from the primary path did a lot better than the one that was right next to it. So I did the same thing with the path amplitudes. So I kept this one at 8 dBs, but then I changed this one from 1 dB to 3 dB and 8 dB. And I used the best case from the last case, from the path delays. And I found that naturally the one with the lowest signal to interference ratio would be the best one to use, because it gave me a much better bit error rate than the one that was a lot stronger. Oops, stuck. Finally, I added a Doppler shift. So I changed the velocity of the Doppler shift. It wasn't present on the earlier two simulations, but I added it for this one. I found that the Doppler shift that was the least velocity tended to do better in the Rician channel, which kind of makes sense. And then I did the exact same thing with the Rayleigh channel, the fading channel. The only difference between the Rayleigh and the Rician channels is that the Rayleigh is a more specific case of Rician where you don't have that line of sight. So I used the same parameters. There's no K factor, so I didn't use that one, obviously. And they're all just kind of secondary paths. So intuitively, I thought this one would be a little worse than the Rician channel. So same setup, 8 dB, 1 dB, and same path delays. And as you can see, they're a lot higher than with the Rician channel. Because we were looking at 15 and less than 1 for the other two. And this one is above 10 for all of them. But still, the one that was furthest away did the best. So that was pretty consistent between the two different fading channels. Then we moved to the path amplitudes. So again, I used 8 and the 10 times 10 to the negative 5 second delay. And the one with the smallest amplitude fared the best too. And then I did the Doppler shift on this one, but it was a little inconclusive because it said the one in the middle did the best. But I think this one might be a little trickier, since generally you would use this Rayleigh simulation when something is like between a bunch of buildings or behind a mountain, and there's going to be multiple different paths probably coming from all directions. So I'm not sure the Doppler part is as intuitive on this part, on the Rayleigh channel, as opposed to the Rician channel. So I can show you real quick. All I have to do was uncomment that, and I was able to run the simulation. So these graphs are all the same. Give me a Doppler spectrum. You can see that the bit error rates are a lot bigger than 0, 4, 2, and 2. They're actually a lot bigger in the Rayleigh channel. Oops. Okay, let's try this again. While that's loading, I can talk about some of these mitigations that are possible. So the repetition encoding is pretty intuitive. It's just repeating the bit more often so that maybe you do get 1 bit error, but then when you take the average of, say, like 5 of them, you can compensate for that error. Equalization is just adding a FIR filter to the front end. So you can train the FIR filter to kind of learn what your signal is going to be looking like in frequency, and you can kind of tell it where to look and what signals to reject. And then the time diversity one, you can have different, almost like an example is the rake receiver. You can have different, like a number of different receivers, and they all feed into the same one, but they all have a slightly different path delay, so that when you add them all up, they technically are out of phase, but it's not a good explanation. They have different path delays, so the primary signal that you're looking for adds up to be a normal signal, whereas all the secondary multipath signals that are always changing, those end up kind of canceling each other out. So the best way to mitigate fading is probably using some type of all three of these. And so here is an impulse response, just to see what it looked like of the Rician channel. And again, we have bit error rates higher than 0, so maybe some of these corrections that I just talked about could be useful in reducing that bit error rate to 0 again and making the channel useful. That's all I got.